Hello and welcome to the CSES problem solving club today. If you can see my screen and if you can hear me, just post a message on chat to let me know that you can hear me fine. That would confirm that my audio and screen sharing is working fine. Thank you, Traxxas, for the confirmation. So now we will begin today's session. The schedule for the upcoming few weeks will be slightly irregular. So that's something you can see on this page. Let me show you how to reach this page. Offpay.cc and then CSES problem solving club and then past and future meetings. So this is going to show the schedule. So we have only two sessions this week where we will look at two problems, Palindrome Pre-Order and Gray Code. Tomorrow we have a book reading session, which is this one, chapter 1. We'll finish chapter 1, and then we have a break for roughly 2 weeks, and then we'll again continue the problem solving sessions. So that's the schedule for the upcoming few weeks. Let us now begin with the next problem, which is Palindrome Pre-Order. And this is a simple problem. We'll spend less time here and we'll try to spend more time in Gray code. So the problem statement says, given a string, your task is to reorder its letters in such a way that it becomes palindrome. That is, it reads the same forwards and backwards. The only input line has a string of length n consisting of characters A to Z. Here's an example of input. And what we need to do is arrange it in such a manner that we get a palindrome. If there are no solutions, print no solution. So that is the goal here. So this is a fairly simple problem. There are many possible ways to create a palindrome. I'll just show one way, which is quite simple. So say we are given a string like this. Now, what this board is showing are all the possible cases that we have to encounter in a specific strategy that I'm using to create palindromes quite easily. So one possible case, or the first possible case on this board, is all characters occur even number of times. So here's an example. So A occurs even number of times, B also occurs even number of times, and C also occurs even number of times, a possible input string. In this case, it is quite easy. What we will do, we will split the characters, the frequency of those characters, into half, and we'll place the first half in the beginning and then the second half in reverse order. So for example, A occurs 2 times, so half of that is 1. We place 1 of A. Then B occurs 4 times, so we place 2 B's. C occurs 2 times, we place 1 C, and then we just reverse whatever we have built so far. And that will be a very simple way to create a palindrome. Now, the second possible case is exactly one character occurs odd number of times. And we can still have a solution because the character with the that occurs odd number of times that we can place in the middle. So, and then the problem reduces to the previous problem. So for example, here C occurs odd number of times. We can place 1 C in the middle, and then we are left with this much. And we know how to solve this already. This is a case of all characters occurring even number of times. So we'll do the same thing. We will do a frequency count, and we will place each character as many times as is the half of the frequency of that character, and then we'll just reverse it here. Now, if more than one character, so this is the third case, if more than one character occurs odd number of times, then we will not have a solution because, and this I'll explain intuitively. Here we have C odd number of times and B odd number of times, and we know that we want to place the character with the odd frequency in the middle, and we can only have one middle. We only have one middle. We can't place 2 characters with odd frequency. So that is the rough intuitive explanation for the last case. If someone has a rigorous explanation, please feel free to go ahead and share it either on chat or by unmuting yourself. So these are the 3 cases that we have to consider, and the code can also be written in many possible ways because it's a problem that has many possible solutions and many ways to write the code. So let me show one So I wrote a code in a different manner, and I found an elegant solution in the CSES website. This is not the exact solution by Needs Jetcop. It's a solution inspired by a solution, and Needs Jetcop is actually part of this club. This user is not able to join our club because of the time zone issue, but this user hangs out in the IRC channel that we have. So the solution is inspired by this user's solution on CSES. So here it goes. So we have a string s and we just read it, and then we do a frequency count. So this is just doing a frequency count. All it is doing is it is treating this array as a lookup table, and for every character we're subtracting it from the code of A to get the index. So the character A will have index 0, the character B will translate to index 1, and so on. And we're just incrementing the value. So it becomes a lookup table. So for example, frequency 3, that is the fourth cell of frequency. Frequency 3 will give us the character, the frequency of the character D. So that's an example. And now we want to find out which is the middle character. There is a possibility that we have an odd frequency, and that would become our middle character. So that is something we have to take care of separately. So initially we are setting middle equals 0 because so this will be the character with the odd frequency. We'll actually put the character code in this thing. So if it is capital A, we'll put 65 in this thing. So that would be a middle character. So 0 becomes an invalid code. No character that we are dealing with has a code 0. So this becomes a good initial value to show that we don't have a middle character at all yet. And then we loop over this frequency table, this lookup table, and look up the frequency for each character. So we are going from A to Z, looking up the frequency for each character. And if we have found a character with an odd frequency, we are noting it down in middle. We're saving it here. And so this means we have found a middle character. Now, if we find another middle character, say we find a second character which has odd frequency, then we will come to this else condition and we'll say no solution because we have found two characters with odd frequency. So when middle is initialized to a character value, that means we have already found a character with odd frequency. So when we find the second one, we print no solution, and then the rest of the code is just printing it out. So what we're doing is we're checking the frequency of each character from A to Z, and we're printing it printing each character half number of times. So whatever is the frequency, we're printing it that many times. And that holds true for the middle character also. For example, say we have a middle character, say D, which occurs 5 times. So that we would have noted as middle character. So D will be the middle character, and we'll print that character 5 divided by 2, and it is an integer division, so we'll print it 2 times. And then we'll print the middle character here, and again as part of this the loop in the other direction, we'll again print D 2 times. So that's how we'll get 5 number of Ds. So that's how it's done. Here we're going opposite in the reverse direction from Z to A, and again we are checking the frequency count and printing it half number of times. So that's the solution. It's a very simple solution, and of course there are other possible ways to write this code. There are other possible solutions too. I'll just take a quick pause here to check if there are any comments. I don't see any comments, so in that case we will move on to the next problem, and this is very interesting. So this is gray code, and this is a problem that has been studied extensively. It's an integral part of electronics studies as well as computer science studies. So it's a very extensively studied problem. We'll only scratch the surface of this problem in this session, but I'll try to go a little bit deeper to explain the various properties of this gray code and how to translate that into code. So let's get started. A gray code is a list of all 2 to the power n bit strings of length n, where any 2 successive strings differ in exactly 1 bit. And I have some examples, I'll show that. The input line has an integer n, so that's the only input. So for example, if you're given 2, we need to print all possible gray codes of length 2 bits. So all possible 2-bit gray codes, that's what we want to print. And here's the output. So we will have 4 gray code, 4-bit strings, because 2 squared is 4. And this is how it looks. If you see, this is not really the normal binary encoding, because in normal binary encoding we will have 0, 0, 0, 1, and then we will have 1, 0. for the number 3, sorry, for the number 2, and then we will have 1 1 for the number 3. Here we have 0 0 0 1, and then this is reversed. We first get 1 1 and then we get 1 0, and you can see this is satisfying this constraint of Hamming distance 1, or another way to say that is that two successive strings differ in exactly 1 bit. So the difference between 0 0 and 0 1 is a difference of just 1 bit. This last bit has been flipped. Now again, from 0 1 to 1 1, there's only 1 bit of difference. This bit has been flipped, and so on. 1 1 1 0, 1 bit has been flipped. And the interesting thing is it is also cyclic. So if you go from 1 0 back to the top 0 0, again only 1 bit is flipped. If you flip this 1 bit, we get 0 0. So that is the problem. So given any n, so if you're given say 4 as the input, we need to print all 2 to the power 4 bit strings for this gray code. So that would be 16 strings. So let us get started. This is a very interesting topic, and I have a lot of boards for this thing. Let me see how much we can cover in today's session. So I'll start with the description of the XOR operator, exclusive OR operator. I'm pretty sure the audience here is aware of it, but just to set the context, I'll start with this. So this is A XOR B. So 0 XOR, this is a truth table. 0 XOR 0 is 0, 0 XOR 1 is 1, 1 XOR 0 is 1, 1 XOR 1 is 0. There are two ways to interpret this table, two intuitive ways to interpret, and both can be useful in different contexts. One is that A XOR B, and I'm using this operator to represent XOR, this plus with a circle. So A XOR B equals 1 if and only if A and B are different. So basically A XOR B measures whether A and B are different. If A and B are same, then it gives us a 0. So that is one possible way to interpret it. Another way is A XOR B inverts the value of A if and only if B equals 1. So for example, regardless of what A is, if B is 1, then A XOR B will be the opposite of A. That's what it means. And we can see it here. Here B is 1, so it inverts the value of A and makes it the opposite. Here also B is 1, it inverts the value of A and makes it opposite. Here B is 0, it keeps the value of A intact in the result. Here B is 0, it keeps the value of A intact in the result. So two possible ways to interpret this. Here's an example worked out. So this is just the XOR exclusive OR operation, which works on 2 bits. When we do bitwise operation in programming languages, we work on a string of bits. So we just apply the XOR operator on every corresponding pair of bits. So here 0 0 gives 0, 1 0 gives 1, 0 1 gives 1, and 1 1 gives 0. Okay, so that is enough about XOR operation. Now we'll start getting into gray code. So these are many examples of gray code. So this is 3-bit gray codes. I've also noted down the binary representation. So normal binary representation would go like this. Will go like this: 0 0 0 0 0 1, 0 1 0 0 1 1, and 1 0 0 1 0 1 1 1 0 1 1 1. It helps if these numbers are very intuitive, sort of memorized. Then it's very easy to compare how the binary code compares with the gray code, and we'll look at it more deeply, how these two codes are related. So there are two analysis we'll do. One would be the direct relationship between this binary code and the corresponding gray code. So you can just take a look at this and convince yourself that this is indeed a gray code, because if you see any two consecutive bit strings differ in exactly 1 bit. So I'll just pick a random pair, take this one and the next consecutive string. So the only difference is in this bit, 0 and 1, that is flipped around. And like I said, it is also cyclic, so 1 0 0, and this also has 1 bit of difference. So two analysis we'll do. One is to see the direct relationship between this binary code and the corresponding gray code. The other is an internal pattern, a pattern that holds internally within the gray code, and that is called the Reflectant prefix pattern. And that becomes a very easy way to generate gray code. So let us look at this Reflectant prefix pattern. I'll take a big table like this. So the Reflectant prefix pattern becomes more apparent here. So this is this is for 4 bits. So since it is 4 bits, we have 16 codes here. And if you split this table into half, so this is where the half is. This is what I've highlighted belongs to the top half, and everything else is in the bottom is the bottom half. Okay, so there is a reflect and prefix pattern going on between the top half and the bottom half, and that you can see here, 7 and 8. Okay, so 7 and 8 have the same last 3 bits. So the last 3 bits are same between 7 and 8. The only thing that we have changed is this prefix 1. And the same holds good for 6 and 9. The last 3 bits are same. We are only changing the prefix here. So that is called the reflectant prefix pattern. So what's going on here, to get this bottom table, we can take all these 3-digit codes and reflect it. So 100 is repeated here, 101 is repeated here, 111 is repeated here, and so on. And after that, we just change all the zeros to 1 in the most significant bit. So that is the reflectant prefix pattern. And we'll start from the beginning. That will actually show that we can generate arbitrarily long gray code using this method. So we start with just 0, 1. So single bit, 2 possible gray code, and there's nothing to do. It's just 0 and 1. So if you're given just 1 bit, we can only have 2 values, 0 and 1. Nothing more interesting we can do there. Now we want to create a 2-bit gray code. So what we do, we take the 0 and 1 and reflect it. We get 1 and 0, and then we prefix 1. So that's the gray code. Now we go from 2 bits to 3 bits. So we have the 2-bit codes already. We figured it out, 0001, 1110. Now we reflect it to 1011, 01, and 00. So it's the first 4 codes reflected, and then we prefix 1. So that's how we have got the 3-bit gray codes, and same for 4-bit gray codes. So for 4-bit gray codes, we have the 3-bit gray code worked out. We reflect all of them, and then we start prefixing 1. So that's how we get all the gray code. And what we have done by doing this explanation is that we have recursively expressed how gray codes can be built, and this could as well be a valid solution for writing the code. So let's see if I have a board to help me out there with the explanation. Yes, I have. Let's see this. Yeah, so what we're currently studying is the patterns that exist internally within gray code. That is a reflectant prefix pattern. We are not really seeing the relationship between the binary code and the equivalent gray code yet. So continuing with reflectant prefix method. And here is a more precise description of this reflectant prefix method. And if you can define it precisely like this, we can also translate it to code quite easily. So here's a notation: G, N, W represent the gray code of N as a W-bit string. So this W stands for the width, or the width of the string. So in this case, for example, here we have width as 4 as an example. So it is quite easy to define the gray code for 1-bit string, right? And that is just Gn, 1 equals 0 if our number is 0, 1 if n equals 1. So I'm using the string notation to say that this is the gray code output as a string, as a bit string. So that is just Gn, 1, which is quite easy. Now Gn, W. How do we get Gn, W? First, we have to decide whether we are in the lower half or the upper half. So that's what we have to decide. So here we are dealing with 4-bit codes. In 4-bit codes, we have 16 possible numbers, 16 possible codes, and anything that is less than equal to 7 is the upper half, or the lower half. We can, okay, upper, all right, I should say it upper half. I think that will be more clear terminology. So, and that condition is explained here. So if this n is less than 2 to the power w minus 1, so if in this case w is 4, so 2 to the power w minus 1, which is 2 to the power 4 minus 1, which is 8. 2 cubed, 8. So if n is less than 8, which is in this area, that means we are working on the upper half. So that's the first condition. The second condition denotes the bottom half, this half, and that is if n is greater than or equal to 2 to the power w minus 1, which in this case is n is greater than or equal to 8. Okay, now what we will do depends on whether we are in the lower half or in the upper half. So if we are in the lower half, what we do, say we want to find the 4-bit, or let me pick this as an example, okay, 5. Let us say we want to find the gray code for 5. Now 5 belongs to the lower half, so there will be no reflection going on. The reflection happens for the, okay, I'm misusing the term lower half because lower can mean this, but I'm talking about in the terms of numbers. So I will use the term upper half and bottom half. So I'll not say lower half. So 5 belongs to the upper half, and we want to get a 4-bit string for it. Since it belongs to the upper half, there is no reflecting prefix pattern going on. It will be just the extension of the 3-bit code that we already know and putting a 0 in front of it. So that's how it works. If, say, we have to solve for 12, which is what I've highlighted here, then since it is in the bottom half, we'll prefix 1 and then we will find its reflection. So it is a reflection of what? It's a reflection of 3. So we'll put 1 and then we'll solve the problem we'll solve the problem of finding 3-bit code for 3. So that's what we have to do. So that is how we are recursively expressing the solution. So here it is specified precisely, and once again I'll compare it with examples. So Gn comma W, if this n belongs to the upper half, then we just prefix 0 and solve the problem for n itself for the next lower bit, which is W minus 1. If n belongs to the bottom half, which is this, then we prefix a 1 and then we solve this problem for the reflected number. And in this case 12, this 3-bit code is a reflection of 3. So how do we find that reflection, this number? It's a reflection of what? What is, we want to answer that what? So it's a reflection of 15 minus 12. It's a reflection of 3. That's how we get it. So the maximum possible integer here minus this number tells us what it is a reflection of. So that's what is expressed here. So we'll prefix 1 and then we'll solve the problem for 2 to the power w minus 1, the maximum possible w bit integer, minus n. That is the number that we're dealing with. And we will find its gray code for the next lower bit, which is w minus 1. So with this simple formula, we have expressed gray codes completely. And we can just go ahead and code this, and this would be the solution itself. So I'll just walk through this recursive solution once. So this is G12, 4. We want to find a 4-bit string for 12. How do we find it? We know that 12 is in the bottom half. So we'll prefix 1 and then solve the problem for 3, and we'll find the 3-bit code for it. And that is what we'll put it here. How do we find 3-bit code for 3? So 3 bits means we are dealing with 8 possible numbers, and 3 belongs to the bottom half, 3 belongs to the upper half of these 8 possible numbers. You can see this 3 is here, 8 is here. So it's in the bottom half, it is in the upper half of these 8 possible numbers. So the solution is going to be just 0 and the 2-bit code for 3. So that's what has happened here. So G3, 3 expands to 0, concatenation, solving 3 with 2 bits. And how do we solve 3 with 2 bits? When we're talking about 2 bits, we have 4 possible integers, and 3 belongs to the bottom half, which means we'll do the reflectant prefix. So we'll put a 1, and that is this 1 coming out because 3 belongs to the bottom half. And then we will solve it for 0 because this code here is a reflection of 0. So we'll solve it for G0, 1, and that we know from this base condition is 0. So that is a reflectant prefix method, and let us see the code for that. Yes, so it is a straightforward implementation of what we have here. This is the function G, the exact G function given here. We're getting 2 inputs, the number and the width. If width is equal to 1, we just translate the number itself as a string. That's what we have done here. If it is in the lower half, if it is in the upper half, okay, if it is in the upper half, we prefix a 0 and then solve the problem recursively for one lesser width. If we are in the upper half, then we prefix a 1 and we solve the problem for what it is a reflection of and one lower width. So straightforward implementation of this. And that becomes a very nice recursive implementation of exactly what we saw so far. Once again, I'll pause here and see if there are any comments about this. Okay, no comments, so we'll continue. If there are any questions, also please feel free to post them on the chat. Now we will take a look at the relationship between the binary code and the gray code. So how are they related? Yeah, Pratik has shared an iterative solution. Let me just take a look at that. Okay, so I'll try to understand this a bit later. It looks a bit different from what I tried, so I'll try to understand this later. Thank you, Pratik, for sharing that. But now I'll continue with what I have planned today. So let us see this. First of all, let me see the solution, because that will set the motivation for what we are trying to do here. So converting an integer n, say to its gray code, is actually quite straightforward. It is just this. There's a very simple Boolean expression for that, and it's a famous expression. It converts any number n into its gray code quite directly. So for example, let me just bring up an example here. Let us take this. So the number 8, the gray code for number 8 is 1100. And we can get that quite easily from this binary code. What we need to do is we need to take this binary code and then we need to shift it right by ones and then XOR both of them. So let me show it here. So this, the gray code for 8, that's what we're trying to work out. Okay, so 1000, sorry, 1000, that's the binary code for 8. And then we right shift the binary code for 8. It becomes 0100. And then we do an XOR. So 0 and 0 similar, so 0, 0, 0 similar, 0, 0, 1 different, so 1, 1, 0 different, so 1. And this becomes the gray code of 8. And if you see, this pattern holds good for everything. So let us take another example. So say 0101, we shift it by right ones. So that would become 0010. And when we do an XOR, we would get this. And so on. So why does this work? And that requires, maybe that's a simple explanation, but I just started with this thing and I was trying to figure out why does it work? Why is it so simple? And it took me, to be able to explain this, it took me about 1, 2, 3, 4, 5 boards. It took me 5 boards to explain this thing. So I don't know if this is the simplest possible explanation. Maybe this is a simpler explanation, but I'll go ahead and share what I have understood. Okay, not 5 boards, 4 boards. It took 4 boards, 1, 2, 3, and 4. Let's start here. So for now, we'll not tackle the entire problem of gray code at once. I'll just build the concepts step by step. Let's start with this. So let us say we have an alternating sequence of 2 symbols, A, B, A, B, A, B, A, B, and say it continues infinitely. And we want to create a reflectant, say reflection of this. So what I mean by reflection is, this is the sequence, right? A, B, and then it keeps repeating. So after it is repeated once, I want to reflect it. So it becomes BA. And then we reflect it again. So AB, which is basically the same thing as saying we bring back the original AB here. And again, we reflect it, BA, and so on. Again, we put AB and then again, it will reflect BA. So can we encode this in a formula? So that's the intention here. So let's just go through this thing, because I wrote this board several weeks back. I don't remember everything, so I'll just read this thing to remind myself and work through this board together. So consider an alternating sequence of 2 symbols, A and B, which is A, B, A, B, A, B. Number the occurrence of each symbol by its position, and we'll be using zero-based index. That makes some of the calculations simpler. So we'll use zero-based index, and fortunately that's also what we use in programming. So that's one of the good side effects of keeping it zero-based. If we pick all positions n, so what we are doing here, to get the reflected sequence, we're flipping some of the symbols. So we are flipping this A to B, this B to A. Again, this A to B, and this B to A. The question is, which symbols do we want to flip? Can we encode that? And that's what we will do here. If you pick all positions n such that floor of n by 2, or in programming terms, the integer division n by 2 is odd, flip the symbols at those positions, and we will get a reflected sequence A, B, B, A, A, B, B, A, and so on. And that's what is happening here. So if you see 0 by 2 is 0, I will do an integer division. So that is implicitly understood now. This is position number 1, so 1 by 2 is 0, and the result is even, so we'll not flip them. This is position 2. 2 by 2 is 1. We're getting an odd result, we'll flip it. And again, this is 3. 3 by 2 is 1. So again, an odd result, so we'll flip this. And if we continue that, we'll get a reflected sequence. So this becomes our base case. So this is something we can confirm by inspection, or we can make a slightly more rigorous argument as well, but I don't think it is necessary for a simple case like this. As another example, let us take this. 6 by 2 is 3. 3 is odd, so we have flipped it. Again, 7 by 2 is 3. 3 is odd, so we have flipped it. 8 by 2 is 4. 4 is even, so we are not flipping it. So that's the thing. And in gray code, when we're generating gray code from binary code, these A's and B's would be zeros and ones. So that's how this whole thing will tie back to gray code later. So in this board, what is important is that this is the formula for flipping. If the position n, if a position n gives us n divided by 2 as odd, then we flip that position, the symbol in that position. And if we do this for all positions, we get a reflected sequence. Now that is the same thing as saying we pick all positions n such that we right shift n by 1, because n divided by 2 is the same thing as right shifting n by 1 bit, and checking if it is odd or not is the same thing as testing its lowest significant bit, whether that is 1 or not. So and that is the same thing as taking this number 2. So let us say this one. Okay, we want to know if you want to flip this. So this is 6, and we want to do 6 divided by 2, which means we take this binary code and we right shift it by 1, then we get just this much, 0, 1, 1. Because we have right shifted by 1, we have lost the last 0, and then we test this bit, the one that is highlighted in green. And if that is 1, then we do a flip. So that is the procedure. So we explained it in 2 different ways, one in a formula manner, another also in formula, but that's something that is more consistent with what we do in programming. Yeah, and I think that is enough. So one thing I must say, that seeing this board and understanding these patterns is of course going to be a personal experience. It is possible that even if I try to explain this, it doesn't make sense. In that case, please go through these boards later. I'm pretty sure it will make sense once you go through this board in your own private time. But I'll just run through this boards at least once to explain what's written in this board. And after that, if someone wants to read this privately once again, that is of course possible by going through this website, offpage.cc/CSES. Now we'll tackle a little bit more difficult problem. Now the problem is we don't have an alternating sequence of A's and B's. What we have is alternating sequence of repetitions of A's and repetitions of B's. So here A is repeated 3 times, B is repeated 3 times, and again A is repeated 3 times, B repeated 3 times, and so on. So I'm noting it down like this: A repeated k times, B repeated k times, and alternating sequence of that. Now, based on what we have done earlier, we can get a formula again for getting a reflected sequence, and the reflected sequence would look like this: A 3 times, B 3 times, and then B 3 times, A 3 times, and it continues infinitely. So once again, this is okay. This is A. So we have this thing reflected here, and then what I've done. Oh, this is a mistake. I should have put A, and then B, B, B. So these rows are a mistake. I will fix that later. So board number 5, I'm just noting it down for myself. Okay. So anyway, just ignore this much, and you can see this much. We have done a reflection here. So how do we do the reflection? The formula is going to be, we pick all positions n such that n divided by 2k is odd. And that follows quite easily from the previous board, and that is explained here. So first of all, let me demonstrate this, that it is really working. So what is k for us? K is 3. right? Because k repetitions, 3 repetitions here. So we want to decide whether we want to flip, say, this one. Okay, so 7 divided by 6, because 2 times k. Okay, so 7 divided by 6 is 1. 1 is odd, so we flip this. So that's what we're doing. How does it follow from the previous board? This follows directly from the previous board if we denote each group of repetitions as a symbol of its own, which is we are denoting this whole repetition 3 A's with A prime and all the 3 B's with B prime. So what we're getting then is a sequence A prime, B prime, A prime, B prime, A prime, B prime, and so on. Then number the alternating sequence groups, that is A prime, B prime, A prime, B prime, by their positions, which is 0 based, and then note that the nth symbol here, so we have split it into groups, right? A prime is a group, B prime is a group. So the nth symbol, the nth actual symbol belongs to n by kth group. So that's what we are seeing here. And we know that we want to flip the n by kth group if n by 2k is odd, and that is from the previous board. So this becomes our group number, and we want to flip an entire group. And how do we do that? We do that by this formula. So we take the number, the position, divided by 2. So if our group number is n by k, we divide by 2, and we get n divided by 2k, and we flip that entire group. And that is how we get reflected sequence for an alternating sequence of repetitions of characters, not just alternating characters. Okay, so this is another result that we have got, that we have to flip the symbols at position n if and only if n divided by 2k is odd. Now, how does it connect with our gray code? In gray code, we will see, or in binary codes, we will see that these repetitions will be always a power of 2. Okay, so let us go back to gray binary codes here. For example, see this binary code, this second column, the one where I'm running this mouse pointer. If you take this bit, this is an alternating sequence of zeros and ones. This one is 2 zeros and 2 ones, 2 zeros and 2 ones alternating. It's a power of 2. The repetition number is a power of 2. This one, 4 zeros and 4 ones, 4 zeros and 4 ones. This one is 8 zeros and 8 ones, and so on. So it's always going to be a power of 2, the repetition number or the value of k. So we have done this analysis for arbitrary k, where k need not be a power of 2. Let us now do it for power of 2, and we will get some nice results. Let us take a look at that. This time k, let k be a power of 2, because that is the kind of repetitions we'll be dealing with in our binary codes. So where r is a non-negative integer, and so k would be something like this, 1, 2, 4, and 8, which would be the repetitions of any column in binary code. Consider an alternating sequence of 2 to the power r repetitions of a, and this is a mistake again, should be 2 to the power r repetitions of b. So while preparing this board, I was going back and forth whether I should keep r as the notation here or r minus 1. I ultimately settled for r as the notation. So this should also be 2 to the power r repetitions of b. And just like before, we'll number the occurrence of each symbol by its position 0 based. So this is at 0 position, this is at position 1, 2, and so on, which is given by these numbers as well as their binary codes. And how do we get a reflected sequence from this? We'll just apply the formula that we have learned earlier. So in this case, k equals 4 because r is 2. So basically 4 repetitions, that is the number we are dealing with. That makes r equals 2 because 2 squared is 4. So what we have to do, we have to pick all positions n such that n divided by 2 times k. So 2 times k, which is 2 times or 2 to the r plus 1, because k is 2 to the power r. That's what we have assumed for notation. So n divided by 2 times k, I'll just say it like that to keep it simple, is odd. So in this case, where you have repetitions, 4 repetitions for each symbol, say we want to understand if you want to flip this. Okay, so 9 divided by 2 times 4, which is 9 divided by 8, and we will check whether 9 divided by 8 is even or odd. So 9 divided by 8 is 1, 1 is odd, so we flip this thing, and that's why we get a reflected sequence. That is the same thing as saying that we take this number 9, we shift it 3 times, and then we see what is remaining. So when we shift it 3 times, we lose all these bits. We are only left with this highlighted green one, and we test if that is odd or even, or if that is 1 or 0. If that is 1, we flip If there is 0, we do not flip. So that is how this thing is working out. So if you're dealing with zeros and ones, not A's and B's, is the same thing. What we will do, for example, say we want to know whether to change the 0 to 1 to get a reflected sequence. We shift it by 3 times, this binary code, and then if it is 1, we flip the 0 to 1, which means we are XORing this bit with this number here, because 1 means we want to flip this thing. If it was 0, we will not be flipping this thing. As an example here, 5, we right shift this 3 times, and then we get a 0, and since this is 0, we don't flip this one. So what we are doing is we are taking this bit and XORing with our symbol. So that is how we know whether to flip it or not. And the interesting thing here is that this column here is the same as this column here, the one that I've highlighted here, this column. So the reflection of this column is just the XOR of this number and the previous bit, by what I explained just now. And that holds good for every column. So in fact, the same thing. If we do the analysis for this column, that would turn out to be, so there are repetitions of 2, and the repetition number is 2. So we will be right shifting this integer 3 times, which means we will be testing this bit. So to know whether to flip this or not, to get a reflected sequence for this column, we take this number, XOR it with the previous bit here, and whatever the result is, we put that. That becomes a reflected sequence for this column, the second column. So all this is summarized once again here. So in the regular binary representation of 0, 1, 2, the rth least significant bit, where r is 0 based, of all integers form an alternating sequence of 2 to the power r zeros. So for example, this one, this is the 0th bit, it forms an alternating sequence of 1, 0 and 1, 1, 1, 0 and 1, 1. So the repetition number is 2 to the power 0. Here's another example that I've highlighted in yellow. So this is r equals 1, the repetition is 2, the repetition number. So yeah, so that's what is written here. So these sequences are represented as columns in the example on the left side of the board. Okay, so for example, the column highlighted in yellow shows that the alternating sequence for r equals 1. So if you're dealing with r equals 1, we have 2 to the power r repetition number of 2. So 2 zeros, 2 ones, 2 zeros, 2 ones. And what does that mean? We will take this number to know whether to flip this or not to get a reflected sequence. We will take this number and right shift it by 3 and then test this bit. When we right shift by, sorry, we'll be right shifting it by 2 because r equals 1 here. Yes, yeah. So it all ties back if you go through the previous board. So here we right shifted by 2 and then test whether this is odd or even, which is the same thing as taking this and XORing it with this. So if we XOR this bits with n, right shifted 2, we're talking about this column now, we will obtain a reflected sequence for this column, the yellow column. And let me show an example here. Let us take this, and okay, this is a big example. Let me take this small example. So we right shift it by 2, and so this will be the last bit, and we'll do an XOR of this and this, and we get the same number. So yeah, that's an example. If we do this for every column, r equals 0, r equals 1, r equals 2, we get a reflected sequence of bits in all columns. So we will be able to reflect each column by following this XORing method, where we XOR the bit in one column with the bit in the previous column. And if you have successfully reflected each column, what we will have in the end is a reflected code, because all the bits will be reflecting all the bits for the number it is reflecting. Yes, so that is it. That is the end of this thing. So that is why this this formula works. It's a very simple formula to convert any integer n to its gray code, which is take the number and then right shift it by 1 and then just XOR it. Okay, so this is where I'll stop. I know that was a lot of explanation, and it also appeals to your imagination to imagine all these things, and it is quite possible that I did not do a great job of explaining this thing, but the boards are archived, and so if you want to see these boards later, and all the explanation is also written down in detail, so you can see the explanation too later if you want to. I will just post the links to this board on chat so that you have a link to it. So this is the link to the board. I'm posting it in chat. And you can just scroll down and look for the gray codes, and all of this explanation is documented and archived there. All right, then. So this is where we will stop for the day. We'll meet once again tomorrow, and we will be going through the book tomorrow. So tomorrow we have a book reading session. We'll be going through the CSES handbook and complete chapter 1. So that's all for now. We meet again tomorrow, same time, 1700 UTC. Until then, take care and goodbye.